So I was inspired to create this talk by a wonderful talk done by Jeffrey Dean of Google, which was sort of a history of Google and Google's infrastructure and how it evolved over time. Towards the end of the talk, there was a very good slide that was shown that had the title Numbers Every Programmer Should Know. Sort of spawned a website that keeps track of these numbers over time. I really love this slide because it explained very simply a concept that I had a hard time explaining to other programmers. So I decided to sort of make this talk to sort of take those numbers, see how we apply them in software, and how we can sort of extend that concept to more specific needs. So the original slide looks something like this. As you can see, it's a bunch of common things that happen in a computer program. Cache hits and cache misses, locking things, copying things to and from pieces of memory. My personal hypothesis about why this slide arose was that there was probably a discussion between two engineers about these two parts of the slide right here. There was probably somebody that wanted a particular service to compress its data on the way out, and there was somebody else that argued that, hey, that's going to be too slow, that's going to slow down my service. And this is how they sort of settled that argument. The interesting thing in this case is that today's answer, the answer when they originally had that argument was to not compress or to compress. And today, it turns out that that's no longer the case. So this is an interesting case where the evolution of hardware has changed the correct answer, so to speak, from a performance point of view. But if you look up and down, you see a lot of common things that you'll do inside of a computer program. You'll see accessing disk here. You'll see compressing things here. And down at the very slowest, as always, is going around the world on the network. And so what do the numbers tell us? They tell us that CPU and RAM is very fast, that locking tends to be very fast, networking inside the data center is amazingly fast. Not so a few years ago, but they've done a really great job improving backplanes and routers to make them go very, very fast. Copying data is still a little slow, but it's still pretty fast. Disks are slow, but they're getting, SSDs are less slow. And anytime you go around the world or anytime you go from data center to data center, it's always very slow. So just like big O notation you use to analyze algorithms, you can do the same thing with performance programming. You can look at the most expensive operation that you are using in a particular algorithm or a service or across your whole infrastructure and do the same sort of complexity analysis on that you would do on in an academic exercise. So let's go back and look at the numbers again. I think the most important column to look at is over here on the exponent. That sort of groups together operations into clumps or clusters that generally operate at the same speed. So you got, notice locking is up here, and that's all in the first order of magnitude. Other things are slower. Accessing disks is way down here in the third and fourth one. Accessing the network at large, very, very slow. So inside a computer, I tend to look at a computer roughly like this. Some of you more clever folks out there will notice that this isn't exactly accurate. The inaccuracy is roughly here. That we should have labeled that north and south bridge. But the more important concept I'm trying to illustrate here is that everything that runs fast runs inside the CPU. When you have to access hardware outside the CPU, it's necessarily slower. And this includes RAM. RAM is still very, very fast, but it's far faster than, say, accessing disks over here or accessing your network. But still, you pay a cost for it. And the speed of a lot of algorithms is very much governed by what level of the cache you're accessing or how far down the cache hierarchy you're actually needing to use to perform your work. So let's talk about how this knowledge impacts how we design an entire infrastructure for a second. So first you have to talk about what is fast. What does it mean to be fast? There's two basic ways that you look at fast. There's latency and there's throughput. Latency is basically the amount of how fast your car is going on a highway. Throughput is how wide that highway is. And often when you're designing a particular piece of software inside your infrastructure, you really need to know, are you going for latency or are you going for throughput? Now, it's important to note when you measure latency, you generally measure latency at a particular level of throughput. So how fast am I responding when I'm getting 1,000 requests per second? Because that profile is going to change as you get higher loads or lower loads. So it's important to know how much traffic you're handling at a particular level of latency. Throughput is generally just measured just all out, whatever throughput you can get. It doesn't matter how much you're sacrificing latency. So I tend to think of these things as either the speed of the car or how wide the highway is. And so that gives rise to two basic patterns that you see in modern infrastructures. Microservices, which have been very popular for a long time, 5 to 10 years or so. People don't often know exactly why they're building microservice architectures. The short answer is to squeeze latency, because latency is how fast you're responding to users, and that is how good your response rate is, which ultimately, theoretically, should lead to more revenue. Not every part of your infrastructure is responding to a human scale request. So some things like the metrics you're gathering, those things will be coming in and you don't really care. There's no response that's happening there. In those cases, you're really not going to worry so much about it. You're just going to be optimizing for throughput. So why do you do a microservice? Well, as I said before, you do it for latency. Generally, this is going to be responding to a web request. There's two basic scales for latency. There's human scale and there's machine scale. So human scale is anything that a human can notice, right? So under 100 milliseconds or so, humans just don't operate that quickly. So as long as you're going that fast, it's good enough. The other one would be machine scale. So that's generally used in finance or high-frequency trading, something like that, where you're trying to beat another programming team. That's a whole different ballgame. And generally, you're going to write the code differently based on what you're doing. The other advantage of microservices is it's nice to break your teams into smaller and smaller groups. If you have a particular team that's only operating 4 or 5 engineers, it's a lot easier to manage than when you have 40 or 50 engineers. So as opposed to data pipelines, applications that are designed to move as much data as possible through some section of your infrastructure. So when you write those, you're generally writing them differently. You're generally going to determine a certain batch size, certain number of requests that you're going to handle at once. You're going to pre-allocate all the resources you need to process that particular group of rows. And then you're going to execute them in those groups. This gives you a little bit simpler architecture. You can get it to go a lot faster. And you operate the machines differently. So in a microservice, you're often operating at 30 to 50% load for the servers. Well, for these machines, you're going to operate them all the way hot, 100%. So when I'm looking at choosing a particular platform, I generally look at 3 different aspects of that platform. The first one I always look at is reliability. So that is basically how often you're processing a row or how likely you are to process a row. Are you guaranteed to process it once? Are you guaranteed to process it at least once? Are you guaranteed to process it at most once? Generally, a system in a particular configuration will give you some guarantee. And you need to identify beforehand what guarantee you need. Because it's very difficult to make a system that doesn't give you a guarantee give you a guarantee. That's particularly difficult. The other aspect of reliability I look at is something known as the CAP theorem. CAP theorem was first stated by a guy named Eric Brewer, who was a PhD candidate at Berkeley at the time. And he basically stated that you get 2 of the following 3. You get consistency, availability, or partition tolerance. Just like in most areas of work, good, fast, cheap, pick 2. Well, in this case, consistency, availability, partition, pick 2. So you have to decide which of these things you're going for, which of these things that is important to you, because you're not really going to be able to make up the third one. If you wanted availability and you didn't choose it, you're not really going to be able to add it yourself. Not without significant time, effort, pulling out of hair, blood, whatever. The second one I look at is durability. And this is basically the ability of the system to function correctly as long as the hard disks don't fail. So if you get crashes, what have you, the data will still be there. So this is generally given to you by a database, something that's ACID compliant. If you need this, it's better to just have a system that gives it to you. It's very hard to build in yourself. And the third one I look at is scalability, which is the ability of the system to handle more traffic with more hardware. Generally, in a scalable system, when you're trying to go for very large scale, you'll have some sort of controller node involved there. In Kafka's case, that would be Zookeeper, something that's managing the metadata of the system. There's generally one or a smaller number of those nodes that are handling that work. And generally, at the highest levels of scale, that is what's going to define how fast that system can run. Sometimes you'll see 3-level systems. Generally, no. Not unless you're working for Google or something like that. So let's talk a little bit more about CAP analysis and the CAP theorem. So you have availability and consistency. That's the most common pattern that you see. That's certainly the oldest pattern that you'll see. Traditional RDBMSs do this. You typically see these in e-commerce applications, other web applications, things that need to provide ORM. This is the most common pattern that you'll see. The second one is availability and partition tolerance. Those are sort of the Dynamo descendants, Cassandra, CacheDB. Those are for when you want the system to always be able to read data or always be able to write data. You always want the data to keep flowing in no matter what's happening. That's really what you get with these kinds of systems. The final one is consistency and partition tolerance. You typically see these in financial transaction applications. These are systems that will refuse to accept new data if something's wrong with the cluster. These are systems that are designed to fail rather than let you do the wrong thing. So when you're choosing a third-party application to use, whether it be an open source or a software vendor, it's all about trade-offs. If there's a particular requirement you don't know about ahead of time, this can significantly throw a monkey wrench into your plans because it's very difficult to take a system that's AP and make it CA. This is probably going to be harder than the rest of the work you have on whatever project that you're working on. So it's better just to choose a system that actually can do this out of the gate. And it's all about trade-offs. There is no perfect system. There is no system that's better than the rest. There are simply systems that give you particular guarantees. And that's what those systems do. And adding extra guarantees to those systems is significantly difficult. So it's important to note what use case the platform was written for. Because when you're writing a platform like that, there's 1,000 decisions that are going through programmers' heads. They're trading off, how reliable is logging versus what should happen in this failure case or that failure case or what have you. And they'll generally have a use case in their head they're writing it for. So you can't really take a system that's designed to be an ETL system and turn it into a really scalable analytic system. You can't really take an analytic system and turn it into a ETL system because they were designed for different things. And tiny little things like how they handle errors, how they handle recovery, those sorts of issues, they just will not be done in the way that you expect them to be done or need them to be done if it was written for use case A and you need use case B. So it's also important to note, does it use disk? Does it use networking? That'll give you an idea what its maximum scalability is. And does it give you the one-to-one guarantees you need, or do you need just more statistically correct guarantees? So how do we use the numbers? So let's talk about one particular use case here. Let's imagine an example application, very simple application. Something that simply takes JSON objects via REST API. It parses the JSON, does a bit of transformation on it, and then sticks it into a database. So say we write this, it works wonderfully, we put it in production, and we're ready to go ahead and use it. We turn it on, it does okay, but it doesn't scale and perform as well as we want it to. What part of the software should we optimize? Does anyone know? Any guesses? Which would be? That's close to correct, yes. That's pretty close to correct, actually. So let's do a little bit of back-of-the-envelope math. So a 40 gig network will run at 5 gigabytes a second theoretically, but in practice it'll run more like a gigabyte per second. So assuming we're using the network for both the in and the out, We're reading in HTTP, writing out JDBC, so we're using both. Well, that means that this networking stack can handle about 250,000 2K JSON objects a second, roughly. Do a little bit more math. 40-core box, parsing a 2K JSON object can do about 30,000 objects per core per second. So a 40-core box can do about 1.2 million per second. So optimizing the parsing or transformation doesn't really do us much good, because the thing that's slowing us down, the thing that's bottlenecking us, is our network performance. So the correct answer in this case would likely be to compress the JSON on the way in, which brings us back to the original numbers. So now let's talk a little bit about blocking versus non-blocking. It was the same decision that the original people that created the chart were going through, whether to do compression or not on the network. Anyway, blocking versus non-blocking I/O. I know a lot of folks love non-blocking I/O. It certainly makes you sound smarter. It's more interesting to write. It's much more efficient. But it's not always better. Sometimes it's worse. This is one of the things that surprised me greatly. These two bars here, that's blocking performance. These two bars here, that's non-blocking. So in some use cases, non-blocking is not just slower. We're talking about, that's a logarithmic scale. That's 100 times. 100 times slower. But when you get up to real world levels of traffic over here, they're roughly the same, except for blocking right. Strangely, it's much faster than everything else. But this doesn't mean you should take your application at home and switch to blocking. That's clearly not the case. This was a micro benchmark. It got to use all the available resources on the box. It used a lot more CPU when it was doing this blocking I/O. It was also writing to a fixed number of file handles, so it was sort of optimized for blocking, sort of cheated a little bit. This is the best case for blocking, but generally it won't be the case that you should use blocking. So when should you use one versus the other? Well, it depends on how many I/O resources you're handling, how many handles you're interacting with, which is basically how many sockets you're interacting with, or how many files you're interacting with. If you're interacting with a very large number of them, you definitely want to use non-blocking I/O. The extra overhead of having those threads blocking and waiting to access those file handles would be much slower. So it would definitely be more effective in cases where you're, say, writing to 40 different sockets or handling 40 different clients. That's going to be way better in non-blocking. But if you're doing a batch application, you're writing one file as fast as you can, well, then you just use a very simple blocking API. And the reason for this is that down at the very lowest level of the stack, all I/O is asynchronous down inside the kernel of the operating system. And so the blocking APIs, there's extra code written by system programmers to give you blocking semantics. And those guys, this is all they do. Somebody sat for a year optimizing the blocking code inside Linux, and they were really smart and really good at it. And it's going to be very difficult for you to achieve that yourself. And they did that for a very specific reason. They did that so that when you're writing out one file, you can do it as fast as possible. So that's what really blocking is for. When you're writing one file, you're talking to one thing on the other end of the network. So I did some more benchmarks for this presentation, sort of additional numbers that should sort of inform this. The core idea I want to keep hammering home in this is performance is about measurement, right? Whether that's profiling or micro benchmarks, which is what I did, it doesn't matter. But it's all about measurement. The hardware will change over time, and the performance benchmarks will change over time. So I'll give you an example. It used to be that matches, well, it's still the case that a match will compile in and call a method called isInstanceOf. IsInstanceOf used to be the bane of Java programmers. You should never, ever call it. In addition to the fact that it's not very OO, you shouldn't do it because it's very slow. Well, turns out that's not really true anymore. It used to be true. I thought it was true when I started writing this presentation. Turns out I was very wrong. Turns out that isInstanceOf is now nearly as fast as an integer comparison, which surprised the heck out of me. I was amazed. So those guys are very smart on the Oracle JVM team, and they did a really good job with it. And I didn't even think that it was possible to make it that fast, but they did. And the only way I found this out is by measuring it. I didn't spend my time digging through the code of the JVM, but I did go in and measure it. Anyone can measure it. You don't have to be an especially great engineer to measure it. And then you can learn, what technique you should use. So it turns out because they did this, that the match statement is incredibly fast. It used to be the case that it was good to do some sort of weird compiler tricks to make it so that when you were matching on a class, there's actually a JSON Scala library that does some very clever compiler tricks to sort of avoid this that will go unnamed. And it gives you some pretty awful compiler errors when you mess up the code or when you import the wrong thing. It's quite frustrating. At one point, that was really an excellent optimization technique. Today, it's just pointless. Some of the other things on here are generating random numbers and getting current time. Turns out they've gotten very fast. The Linux syscalls are very fast nowadays. Down here, this is constructing a case class with 4 arguments. That's actually kind of slow, especially when you compare it with how fast a lock is. You would have to contend for a lock a lot to make it so that copying data is faster than locking. Interacting with the file system is the next level, so that's a little slower. Here's a context switch, which is roughly as fast as interacting with the file system. That should sort of let you know how expensive context switches are. And then down here at the bottom, some interactions with various data containers. You should see that map is incredibly fast. You would expect it to be incredibly fast. Array is pretty good, but it starts to fail when you get this many elements, so it doesn't go quite as fast. But because it's so memory efficient, it does pretty well. And list is so slow that you shouldn't even bother with it. Not if you have a lot of pieces of information in there. So let's talk about a couple other programming techniques. Let's talk about recursion and loops. Now, I measured while loops versus for comprehensions versus recursion versus tail recursion. So it turns out that while loops and for loops and tail recursion are all roughly the same speed when you have small numbers of elements. But this might come as a surprise to some of y'all that it turns out that while loops are significantly faster in very large numbers of iterations, about 30% faster, in fact. So I know some of you functional lovers out there would rather lose a finger than write something like a while loop, but when you're on the inside of your inner loop and you're trying to squeeze every last microsecond of latency out of there, you might want to think about switching a for comprehension to a while loop, especially in a loop where you have a lot of things you're iterating over, if you're looping over that many, many times. Now, it's also important to note that I measured these with Scala 2.11. I might be wrong. Scala 2.12's come out. They might have made for comprehensions faster. So somebody might take the code, download it, run it on Scala 2.12, and come out with, well, turns out for comprehensions are now just as fast as while loops, at which point my advice now is useless. But until somebody measures it, nobody knows. So caching is another useful technique. Caching is almost always a good idea. The only time caching is not a good idea is when it's going to fill up a particular level in your CPU cache. So if, for instance, you fill up all of L3 and you can't even fit the cache into L3, caching is not going to work in those cases. But that's very rare, and generally you're not going to worry about it too much. Caching is almost always a good idea. Talk about different collections. We measured array and map and sequence and index sequence. We didn't measure list because it was so slow. The thing to note is that because array uses less memory, it's actually faster than map for small numbers of elements. Something less than 500 or 1,000 elements in your list, you should use array all the time. And if it's bigger than that, you should use map all the time. Turns out those are the fastest data structures. The only time that's going to be not the case for a larger data structure is there will be cases when array fits in one level of the CPU cache and the map doesn't because it takes twice as much memory. In those very strange, very rare cases, array will even be faster than map. But that's not going to happen too often. So the final one we'll talk about is mutable versus immutable. So I know everyone loves immutable data structures. They're easy to program for. But it turns out that mutable inserts are 30% faster. Surprisingly, immutable removes are faster than mutable removes. It's very weird. But generally, you want to use, the lesson I drew from this is that you want to use mutable data structures when on each request on end, you're generally going to do one write to the container. So if, for instance, you're going to end up doing something where you rebuild a cache and you do 5,000 writes and then you do 10 million reads, use immutable. Well, you're going to use a builder in that case anyway, which is still a mutable data structure. But at the end, wrap it in immutable, and that will be all will be good. But in the case where you're doing an LRU cache and you're moving things from the cache as you're inserting into the cache, in those cases, it's probably better to use mutable. Another thing to consider is the type-safe folks are very smart. They're very good programmers. They don't have a lot of resources. They spend a lot of time writing the mutable data structures. They did that for a reason. The reason is this particular use case where you get a read and then you do a write, and then you do a read and then you do a write. That's when you want to use mutable. And the final concept we'll talk about today are inner loops. So not all lines of code are run the same number of times. Some of them are run, generally you'll have a basic pattern in software where you have some initialization. You have some teardown code at the end. And in the middle, you have code that's run over and over and over again. That's the inner loop. The truth is that a database is the ultimate example of this. In a database, about 90% of the code only runs when the query is executed, not on every row inside the database. 90% of the code, all it does is try to figure out the exact fastest, most efficient way of processing individual rows inside the database from the table. And they basically spend 90% of the time writing code that doesn't run per row for the data that's coming out of the database, or the data that's going into the database for that matter. This is basically what you would expect from 40 years of optimizing one architecture. So let's talk about how you might optimize a particular inner loop. One technique is splitting an inner loop into two of them. If you have an inner loop that uses a lot of memory, it might be better to do this because you can fit more rows in cache. You want to amortize expensive syscalls. Maybe you're creating files or something else that's rather expensive. You want to try to do that once at the top of the loop and then just reuse that handle if at all possible. You want to remove ifs and non-inline function calls. To figure out if something's not inlined, you sort of need to use Java P and some other fancy tricks. Consider using an API for parsing that does callbacks instead of giving you a DOM. The DOM uses a lot of memory. Callbacks are just going to use as much memory as they need to perform that particular callback and then free that memory or reuse that memory. They're generally a lot more efficient. And then you want to hoist constants and static computation out of that loop. The compiler will hoist simpler things for you, but there's only so much it can do. And so how does this help us design software? Well, the first thing is you need to understand what you're doing. Are you doing high throughput or are you doing low latency? So that's going to inform what platforms you're going to use, what libraries you want to use. Cache when possible, use array for large use map for large collections, use array for small collections. And you only want to bother with optimizing the inner loop. The final thing is your hardware may be different from mine. So if you don't believe a number in here or you think it's different, maybe it is. Rerun it on your hardware, find out, let us know. We're going to keep those numbers up to date. We are sharing it on GitHub right there. And send me a PR if you don't like how I wrote some of the code. Anyway, thank you for your time.